You guys can hear me locally, that's good. Okay, so we were partway through this problem at the end of last class. We were asked to find the moment of inertia about the x prime and y-axis. So first we found the centroid, so we knew where to draw this x prime axis. So the centroid was found to be 170 millimeters above the x-axis. That's where y bar was. And now we're ready to fill in the second table. So it's not a very big table, there's only two sections. So where is y bar prime going to be? That's going to be the location of the center of each section measured from the x prime axis. No, not 0. Because it's the center of each section. So for the first section, it's going to be 150 above the bottom of the rectangle, but the bottom of the rectangle is at negative 70 from the x prime axis. So we've got negative 70 plus 150. That would be 130. Why can't I find... Oh, there we are. No, that's not right. Negative 70 plus 150? That'd be 80. Yeah. That would be 80. And that's going to be all in millimeters. The moment of inertia of the first rectangle about its own centroid, so that's the 1/12 bh cubed. Put that in up above. And the moment of inertia about its own y-axis is going to be 1/12 b cubed h. Those are from the tables at the back, or they're good ones just to remember. All right. So here we have 1/12 times b, which was 100, times h, which is 300 cubed. Is anybody calculating it? I haven't got a calculator. .25 times 10 to the 8. And that's going to be millimeters to the fourth. And then the 1/12 b cubed h should be 1/9 of that, shouldn't it? It isn't, though. Oh, b is the width here, which is going to be 100. H is the height, which is 300. Yep. Pardon? That is a 9th, yep. And then we're going to use the parallel axis theorem to figure out the moment of this section about the centroid of the object, so using this distance. So that's going to be this amount plus, this amount, the 2.25 times 10 to the 8, plus 80 squared times the area, which is up here, 30,000. Anybody else get? Yeah. Okay, so 4.17 times 10 to the 8. And we do the same thing with the second section. Where is the centroid of the second section measured from the centroid of the composite? This is at 170, and this is going to be at 50. So that'd be at negative 120. Although if you put in positive 120, you're going to get the same result. But technically, it's 120 below. Okay, and we're going to calculate these using the same formulas. So the 1/12 BH cubed. B is 200 this time, and H is 100. What did you get for the Y? Okay. And then parallel axis theorem to find the moment of inertia about the centroid of the composite. So that's going to be the 1.67 times 10 to the 7 plus 120 squared times 20,000. 3.05 times 10 to the 8. All right, now what do we do? We're trying to find the moments of inertia about the x-axis, the y-axis, and the x-prime axis. Not necessarily in that order. So we're going to add up these two, and we're going to add up these two. Just the last two columns. These would be meaningless sums, so we wouldn't add them up. So for the IY, and you notice we didn't have to figure out x bar for any of these because they were all 0. It's symmetric about the x-axis. That made it easy, relatively. So if we add those up, that should give us 9.17 times 10 to the 7. And if we add these two up, 7.22 times 10 to the 8. And those are both in millimeters to the 4. So that is the moment of inertia about the y-axis, and this is the moment of inertia about the x-prime axis. So how are we going to find the moment of inertia about the x-axis? Well, I could redo the table and measure the distance from the x-axis instead of the x-prime axis. But that wouldn't be the smart way of doing it. We would be smarter to use the parallel axis theorem. Fewer calculations. So I x equals I x prime, the moment of inertia about its centroid, plus y bar squared a. So that's going to be the 7.22 times 10 to the 8 millimeters to the 4th, plus y bar for the whole composite is what we calculated here, the 170. So we have 170 millimeters squared times the total area, which was 50,000. Millimeters squared. Yep, which we calculated up here. That's what I have as well. 2.17 times 10 to the 9th millimeters to the 4th. All right, I only have one example problem left, and that's this odd shaped, kind of like an I-beam, except instead of the tops being rectangles, they're circles, the top and bottom, and they're not the same size in this case. So we want to determine the moment of inertia of the beam's cross-sectional area with respect to the x prime axis passing through the centroid of the cross-section. And we're lucky in this case because we don't have to find y prime, it's given in the problem. Y prime is given as 104.3. And that's going to be millimeters again. All right, so what's the first thing we should do? Section it. Okay, so what kind of sections should we have? Right, so if we work from the top down, if this is 1, this is 2, and this is 3. And we're going to ignore the fact that these are actually going to be curved ends on the rectangle. We're going to ignore it because it's going to be so small that our safety factor would more than account for it. Right? It's going to be like a fraction of a percent. So for each one of these areas, we're going to need to calculate the surface area, the centroid, and the moments of inertia. So we haven't done any circles yet. I'm pretty sure everybody knows the formula for the area of a circle. Okay, so that's going to be pi r squared. And r is going to be 17.5 millimeters, since it's a diameter of 35. 962 millimeters to the 4th. Oh, squared, yeah, I'm getting ahead of myself. How are we going to find the moment of inertia of the circular area? Formula from the back of the book. So if we flip to the back of the book, you see there's a circle right there. So zoom in. So it confirms the area is pi r squared, and the moment of inertia is 1/4 pi r to the 4. That's the moment of inertia of an x-axis that goes through its centroid. So 1/4 pi r to the 4. Actually, let's cut that out and paste it in there, just so we remember. So again, the radius is going to be 17.5 millimeters. 73662. This one is millimeters to the 4th. Okay, one last number that we need for this shape, and that's going to be y tilde. So y tilde is going to be measured from this axis. And this axis, let's see if we can figure this out. So this total is 150, plus the 50 means this would be at 200 from the bottom. and we're starting at 104.3. So this should be 200 minus 104.3 and plus the radius of the circle. And that's going to be just millimeters. Okay, that's what I got as well. So for shape number 2, that's going to be easier. A equals BH. Base is 15 millimeters. Height is 150. 250 millimeters squared. Moment of inertia about its centroid x-axis is going to be 1/12 BH cubed. 4218660. So 4.8600. 4.2186 times 10 to the 6. That's millimeters to the 4th. And its centroid is going to be 75 above here, which would make 125 over the bottom minus the 104.3. So 125 minus 20.7. All right, and then our third shape is another circle, pi r squared. This time the radius is 25 millimeters. (1,963 millimeters squared). Moment of inertia about its centroid x-axis is 1/4 pi r to the 4, same as the other one. Oh, different radius, same formula. Millimeters to the 4th. And it's y tilde okay, so that would be negative 104.3 plus 25, or 25 minus 104.3 equals negative 79.3 millimeters. So with that data for each of the 3 areas, now we can complete the table. So we're going to have section, area, y tilde, I bar x prime, and then I x prime. I should probably spread those out a little bit more. Okay, so section 1 had an area of 962. Area 2 had an area 2,250. Area 3 was 1,963. Y tilde for area 1 was 113.2. Area 2 was 20.7. And for area 3 was minus or negative 79.3. Our moments of inertia through the centroids of the sections were 73662. And then 4,218,600. These are in millimeters to the fourth. And then our last one was 306,800. Then we're going to use the parallel axis theorem to fill in the last column. Okay, that's what I have. 1.24 times 10 to the 7. And the next one.
5.18.
Okay, that's the bottom one, right? I don't think so. That's not what I have either. I do have 5.18 times 10 to the 6 for the bottom one.
Yeah. 5.18 times second.
For the bottom or for the middle? Really? Okay. What have you got for the bottom one? Okay, that's, I just have them in mixed up order then. 1.27 times 10 to the 7. I have the same values. Okay, so when we add them up to find the moment of inertia for the composite area. How do we, okay, I'll just, so the question was, how do we get the last column? And the last column, again, is this is the parallel axis theorem. These are the moments of inertia about the centroids of the individual pieces. So now I need to make those moments of inertia about this centroid of the composite. So that's why we're calculating this y bar. So all of these values are from the parallel axis theorem. So it's going to be this plus this squared times this. Okay, the only time that we didn't have to do that was when we were doing the moments of inertia about an axis which is goes right through the middle of all of the objects. Like if I was calculating the moment of inertia about the y-axis, in this case, the y-axis is the y-prime axis for all of the pieces. So I wouldn't have to use the parallel axis theorem at all. Normally we are going to have to use parallel axis theorem. All right, so this finishes the last, or at least the part of the last chapter that we're responsible for the final exam. I do have, I have an old final exam here that we can work our way through. This is the 2006 exam from UVic. So it's authentic. This is kind of my template for what our final exam should look like. So it's got 6 questions, and they cover mostly the last half of the course. But then there's some questions like the first one here that goes back to the first half of the course as well. So in this question, question?
Oh, we just lost our data screen.
Oh, okay, let me see if I can get it back for you. Nope, still nothing? Oh, nope, you got a green screen now. Let's try to get to it again. What can you see in Campbell River now? Can you see it?
No, it's just green.
It's just a blank green screen?
Yeah.
Harry? Oh, okay. Okay, so we lost Campbell River for a second. They'll be back. Hopefully we can make it through without too many further disruptions. All right, there we are. Okay, so the first question on this exam has a bent rod supporting 2 forces as shown in the figure. The forces are defined by F1 equals 250 newtons times I hat, so along the x-axis, and F2 equals negative 400 newtons K hat, so in the negative Z direction. Replace the 2 forces with a single equivalent wrench. For this single wrench, be sure to provide A, the Cartesian components of the force, B, the magnitude of the moment, and C, the location where the wrench intersects the XY plane. So, how would we begin this question? Right, so part A is actually, it's the easiest one. I only have 2 forces to sum, and they're already along the axes, so if I add those 2 forces together, I'm going to end up with 250 I hat minus 400 K hat newtons. Okay. Now it gets more difficult. Now we need to find the magnitude of the moment, or we need to find the Cartesian vector for the moment. How are we going to find the moment? Well, also in this case, it's not as difficult as it could be because both of these forces that are acting on the rod are acting at the same point. So I can basically just treat them as one force and calculate the moment about the origin as a cross product of that force and the position vector of C. So that would be RC cross FR. All right, so Cartesian cross product, what's the easiest way to calculate that? Yeah, I would do it as a determinant. So we would put the I hat, J hat, K hat on the top row of the matrix. The components of the position vector on the second row. So the position vector here at C is, looks like 0.8 along the x-axis. Sorry, on the x-axis, 0.5 plus 0.4, 0.9 along the x-axis. I should look at my notes. Right, it's 0.5 to here, and then another 0.4 to here. So positive 0.9 meters. Along the y-axis is going to be the 0.8 meters. And along the z-axis is going to be positive 0.35 meters. And then our resultant force, 250, 0, negative 400. I'm just going to add that vector in here. Oops. All right, so to find the x component, we would put our finger over the first row. We're going to do cofactor expansion along the first row. So we put our finger along the first column and the first row, take the determinant of what's left. So it'd be 0.8 times negative 400, negative 320 I hat. And then J hat, we would put our finger across the second column, take the determinant of what's left, and then multiply by negative J hat, because it's in an odd position. So 0.9 times 400, that's 360 minus 250 times 0.35. Yeah. And is that positive or negative? Positive. J hat and K hat, and take the determinant of what's left here, which looks like negative 4.8 times 250, negative 200, yeah. And that's going to be in Newton meters. All right, so we're trying to find a wrench. We have the resultant force and the resultant moment. What's the next step? Not yet. The next step for finding a wrench is to break the moment down into parallel and perpendicular components. The component of the moment that's parallel to the force, can't do anything about it. I can't relocate the force and change the magnitude of that. But the component of the moment that's perpendicular to the force, by moving the location of the force, I can eliminate that moment. So we'll find the parallel component first, and then the perpendicular component by subtraction. So the parallel component will do basically a projection. So MR parallel. How are we going to find the projection of the resultant moment onto the force vector? Right, we're going to do the dot product MRO dot FR. We're going to divide by the norm of FR, the magnitude of FR. It is going to be squared because I need to then multiply it by FR again to turn it back into a vector. This gives me the magnitude, and then I multiply by the vector divided by its norm again to turn it back into vector form. All right. So if we're looking at the dot product, I'm going to take 250 times negative 320 and then subtract 400 times negative 200. That's right. So there is no parallel component. It makes our life easier, because now the perpendicular component is just the resultant component. It's a zero vector, and that's just going to be the resultant moment. So now, how am I going to find, actually before we go here, they wanted to find the magnitude of the moment. So we're going to need to find the magnitude of the moment, which we have as a Cartesian vector already, and then the location where the wrench intersects the xy plane. The magnitude of the moment, you just use the Pythagorean theorem. So 320 squared plus 447.5 squared plus 200 squared. 585 Newton meters. Now, how are we going to find where this intersects the xy plane? Well, if we're trying to find where the wrench intersects the xy plane, we're basically trying to find out where we would locate the resultant force on the xy plane so that it produces the resultant moment. Or in vector form, we would write our resultant moment, or the perpendicular component of the resultant moment, which in this case is the whole resultant moment, is going to equal the position on the xy plane which would be xi hat plus y j hat cross product with the resultant force. So we have the vector we calculated above, negative 320 I hat plus 447.5 j hat minus 200 k hat is going to equal the cross product. So write it in determinant form. Position on the xy plane is xy 0. The resultant force was 250, 0, negative 400. If we simplify this, we're going to have negative 400y times I hat plus 400x j hat and then minus 250y k hat. How are we going to solve it? I got 3 equations with 2 unknowns. So we're going to solve the first 2 and use the last one as a check. So the first equation would be the I hat terms. So basically we have y equals negative 320 over negative 400. Should be 0.8. Right? Yep, okay. X is going to equal 447.5 over 400. And then our last one, which is a check. It's only a check for y, but at least it's a check. Would be y equals negative 200 over negative 250, which is also 0.8. So the check works. So we've basically found the wrench. The wrench does not have a parallel component of the moment, so it's just a single resultant force that's located at 0.8, 1.12, 0. That's going to have the equivalent force and moment as the situation that's given here. All right, how's our time? Oh, lots of time. All right, so our second question is from the last chapter, right? So it's asking to find the moment of inertia of the shaded region about the horizontal x-axis shown. So the x-axis here goes through the center of the circle. And then second, moment of inertia of the shaded region about a horizontal axis passing through the centroid C, which we need to find first. Yep. You lost contact again. Okay. Harry? I'll try and fix it myself, but usually it doesn't work. You got the green screen of death again. Did you see the shape before we lost the content?
We lost it midway through the last question, but we can see on your screen.
Oh, okay. Can you see the shape behind my head?
Yeah, we just can't tell you the numbers.
Just okay. Well, I'll try and fill in the numbers then as we go.
It's zoomed in, it's good now.
Okay. So, how would you like to start? We would want to split it into sections. So we can answer part A first, and then find the centroid, and then do part B, or we could kind of do it all at once. It doesn't really matter. We'll do it in order here. So where would you like to draw the sections?
Semicircle at the bottom, then this circle at the middle, and then triangle.
All right, so we have quite a few sections to draw here then. So you want to do a semicircle at the bottom, which would have a radius of 300 millimeters, a circular hole at the origin here, which has a radius of 100 millimeters. And then you want to divide the top trapezoid into a rectangle and two triangles. So I get five parts. So if we label those, we have 1, 2, 3, 4, and 5. And even though we have 5 parts, by symmetry, 4 and 5 are going to be pretty easy they're going to have the same centroids, the same areas, the same moments. All right, now what? So our next thing is, right, so I think I'm going to create a table because I'm going to have 5 different things to put in there. So each one of those sections, we're going to need to calculate its area. The distance from the x-axis to its individual centroid. The moment of inertia about an x-axis through the centroid of the part, and then by parallel axis theorem calculate the moment of inertia about the x-axis. So that's the 1/12, or sorry, it's not 1/12. That's the I bar x prime plus y tilde squared times the area. So 1 is a semicircular area. So the area of a semicircle would be 1/2 pi r squared. $141,000. That would be millimeters squared. And where would its centroid be? It's not at the center because it's a semicircle. something like that. We'd go to the back cover, and we'd look. Here's a semicircular area, and the centroid from the axis that cuts the circle in half is at 4r over 3 pi. So that's the value of y tilde we're going to use for the semicircle. 4r over 3 pi. Oops.
Will you use the 300 radius, or will you use the radius 300 minus 3?
No, we're ignoring the circle because we're going to do the circle separately as a cutout. So the radius is the full 300 millimeters. We're ignoring the fact that there's a hole in the middle of it. Because the hole in the middle is area 2, or section 2.
3 minus that area.
Yeah. Pardon?
I'll do it 4 pi over 3 pi.
Oh, 4r over 3 pi.
327.
Let's see what I got before. 127. And that's actually going to be negative, but it's not going to matter because we square it. But it's below the x-axis. The moment of inertia for the semicircle is something we derived before, but it's also in the back cover. And it's 1/8 pi r to the 4. Three 3.18 times 10 to the 9. That's in millimeters. Millimeters to the 4, and then just apply the parallel axis theorem. That's millimeters to the 4th as well. Section 2 is the circular hole. So its area is pi r squared, but it's negative. The radius is 100, so 100 squared would be 10,000 times pi, negative 31,416. Where's its centroid? It's right at the origin, so it's going to be at 0. Its moment of inertia is 1/4 pi r to the 4. It's also going to be negative. And parallel axis theorem, because it's on the x-axis, is going to be the same value. Okay, area 3. Area 3 is a rectangle. The rectangle has width of 300 millimeters and height of 600 millimeters. .8 times 10 to the 5, or 180,000 millimeters squared. Its y tilde is going to be at half of the height of the rectangle. It starts at y equals 0, so it's going to be 300. And then its moment of inertia is going to be 1/12 bh cubed.
That's the point.
5.46 times 10 to the 9? Oh, 5.40 times 10 to the 9, sorry. And then parallel axis theorem.
2.16 times 10 to the 9.
All right. Section 4. Section 4 is going to be a triangle. So it's going to be 1/2 base times height. Its base is 150 and its height is 600.
25,000.
Its centroid is going to be at 1/3 of the height, which should be 200 millimeters. I got millimeters already there. Its moment of inertia for a triangle is in the table. We need to find it. I don't think we've done a triangle yet. There it is, 1/36 bh cubed.
Nine times 10 to the 8.
So sorry if it goes
9.00.
9.00 times 10 to the 8. And then parallel axis. All right, and 5 is exactly the same,
2.75.
which is 2.7, 2.70. So this is also 45,000, also 200, also 9.00 times 10 to the 8, also 2.70 times 10 to the 9. So if we add all of those up, that should give us our moment of inertia about the x-axis. 3.24 times 10 to the 10 millimeters to the 4th. That's part A done. So for part B, we want to find the moment of inertia about an axis through the centroid. So the first thing we need to do is find the centroid. And then the second thing we could do is we could repeat all of the calculations using the different distances from the parallel axis. Or, a better solution, apply the parallel axis theorem to the results from part A. In either case, the first thing we need to do is find where the centroid is. So we need to find y bar. So we're going to be using a lot of the same numbers that we had from the other table. In fact, we could probably just add another column. No, I'm going to do it this way. So we're going to have section y tilde area y tilde times area. Right, and the reason we have those columns in our table is because y bar equals the sum of the y tildes times the area over the sum of the areas. So section 1, we've already calculated its y tilde. Is negative 127. This time it does matter that it's negative. Its area was 141,000. And if I multiply those two together, 1.791 times 10 to the 7. Area 2 was the circle, so it had a y tilde of 0. It had an area of negative 31416, 31,416 times 0 is 0. 3 is the rectangle, plus 300. And its area was 180,000. Multiply those together.
5.40.
Okay, and I'm going to do 4 and 5 together. Since they have the same y tilde, which was 200, they had a combined area that would be 90,000. Which should be 1.80 times 10 to the 7. Okay, and we'll add up the last two columns.
One tilde times the area was 5.41.
Right, because these two almost cancel each other out.
Yeah.
379,600. Sure. All right, so that means our y bar equals 5.41 times 10 to the 7. Hundred and 43 millimeters. Okay, but that's not what we're asked for in Part B. We're asked for the moment of inertia through the axis that's at y equals 1.43, or sorry, 143 millimeters. How are we going to find that? Parallel axis theorem. But this time we're trying to find Ix prime. So we would take Ix and subtract y bar squared times the area. So Ix we calculated before was 3.24 times 10 to the 10. Millimeters to the fourth. Y bar was 143 millimeters squared times the total area, which we just calculated, 379,600. 2.47 times 10 to the 10 millimeters to the fourth. All right, we're a third of the way through the exam. We're making good time, yeah. The next question says, the bucket of a bulldozer and its contents have a weight of 10 kilonewtons and the center of mass at H. Just scroll down a little bit so you can see there's H. Arm ABCD has a weight of 2 kilonewtons and a center of gravity at B. So A, B, C, D. So this part, center of gravity at B. And arm DEFG has a weight of 1 kilonewton and a center of gravity at E. The weights of the three hydraulic cylinders can be ignored. For the equilibrium configuration shown, calculate A, the horizontal force P required in cylinder JC to hold the assembly up, B, the force in cylinder EI required to hold the bucket up, and C, the force in cylinder BF required to hold the arm DEFG up. So we're looking for this horizontal force, the force in this hydraulic cylinder, and the force in this hydraulic cylinder. Where should we start? Okay. Are there any two force members? Right, the hydraulic cylinders are going to act as two force members. And that's because they have pinned ends on both ends are pinned, and there's no other external forces acting on them. Okay, now where would we go next? Okay, what would you do a free body diagram of? Well, it depends if we want to answer the questions in order, because we can actually answer the first part by doing a free body diagram of the whole assembly. So if I do a free body diagram of the whole assembly, I'm going to have three weights that are acting on it. I'm going to have the horizontal force P that's acting on it, and then I'm going to have only two other components of reaction. Where are they going to be? I'm going to have X and Y components at the pin joint at A. Okay, so I could do that. I could also start at section B. So start at the bucket. If I start at the bucket, it's got one weight force acting on it. What other forces would be acting on the bucket? Right, we have the force from the cylinder, EI, and we'd have reactions at G. So since we're asked for everything, I think I would start with this one and then work my way back towards A, so that the free body diagrams would be getting simpler, rather than do one that's the whole thing. So I would start this free body diagram of the bucket. So sorry, on your exams you won't be able to just cut and paste like that. You might actually have to draw it, but the sketch does not need to be pretty or even necessarily accurate, as long as the dimensions can be labeled on it. And the parts labeled so that I can correspond G to G, H to H, I to I. So what forces are going to be acting on this bucket? So we said the weight, which acts through H. Which was its center of mass. And we were told that it had a weight of, the bucket and its contents have a weight of 10 kilonewtons. Okay. Reactions at G, which it's a pinned joint, so it could have X and Y reactions. I'm pretty sure the Y reaction is going to be up. The X reaction, I think it's actually going to be right. But if you don't know, draw it in a positive direction, and if it comes out negative, then it's in the opposite direction. What about the force at I? Is that cylinder going to be in tension or in compression? It's going to be in tension. Again, if you don't know, then guess, and if you guess wrong, you'll get a negative answer. So that would be FEI, and this would be GX and GY. All right. Any other forces acting on the bucket? I've got 3 unknowns and 1 known force. So we would go to equations of equilibrium. What are my equations of equilibrium for the bucket going to include? Forces in the x direction equals 0, and there are only 2 forces in the x direction, so it would be gx minus FEI. Forces in the y direction equals 0. There are only 2 forces in the y direction, gy minus 10 kilonewtons. And we need a third equation, so we need to take a moment equation. Best place to take the moment, not the only place to take a moment, the best place to take a moment would be at G, because that eliminates two of our unknowns. So we have two things that are producing moments. Pardon? GY is, yeah. So FEI is going to give us a positive moment, and its lever arm, how are we going to figure out its lever arm? We do have to look at the original diagram, because this is straight across from here, which means this is 0.6 or 0.6, so that's 1.2 up, and that's 30 degrees from vertical. So what we have is a triangle here. This is G, this is E, this is I, and this is 1.2 meters. So to find this distance, it's going to be 1.2 cos 30. 1.039. So this is going to be 1.039 meters times FEI. And I have a negative moment from the weight. Perpendicular distance is 0.3 meters times 10 kilonewtons. So if I solve that for FEI, 2.887 kilonewtons. Solve this one for GY, which is a trivial solution, but GY is 10 kilonewtons, and GX is 2.887 kilonewtons from here. All right, so we've solved for equilibrium on the bucket, and it looks like that's as far as we're going to get today. So we're going to continue on this exam on Thursday. I'll post, I have a 2005 exam from UVic as well, so I'll post both of the exams. I'll send them to Jim so he can post them to the Moodle site at College of the Rockies, so you guys have copies of the exam. And we'll just continue working through.
Are there exams open back in class?
I don't know.